Assalamu alaikum class. In today's lecture we will see some applications of recursion and we will solve some example for better understanding of this topic. Most common use of recursion is when some kind of backtracking or reversing is required. One such application of recursion is reversing a list, and we will implement the same function using the recursive technique. For example, if there is a single linked list with data item 6, 10, 14 and 20 and user want to print out list in reverse order. So can you write its code that is efficient and without recursion? The answer is yes. We can write an algorithm, but it will not be an efficient one. As we need to print the last element first, we will traverse the list until the last item is found, then print it. And to print the second last item, we need to again traverse the list from the start. As we know, we cannot move backward in singly linked lists. So now we will use recursion to solve this same problem and check whether recursion can give us better solution or not. This is a pseudocode of recursive function that traverses a list in reverse order. It contains one if-else structure. It has two parts. The one is base case, that is a noun solution or stopping condition. Another is general case. If list object pointer that will point start or head node of the list is equal to null, it means that your list is empty or you have reached the end of the list and it will return. That is our base case or stopping condition. Else part is general case, in which we will call the function again by giving it an address of the next element, and this will continue calling the function again and again with the next item until we reach the end of the list. Notice that the statement that print the data will not be executed until we reach the noun solution or base case. We will solve this example to get better understanding. Here is the dry run of the recursive function that will traverse the list in reverse order. So address of the first node is assigned to the list pointer at the time of function calling. So list is pointing toward the first node that contains the data item 6. We will check the if condition. Now if list is equal to null ptr, no, list is not equal to null ptr, so else part will be executed. And the first statement in else part is the recursive function with next data item 10. Note that next line that print the value of 6 will not be executed. All the remaining statement in this function call will be suspended and all the information related to this function will be saved in stack frame. Now we will continue with the next function call, that is with data item 10. We will execute the remaining part when function call with print reverse 10 is completed. So now list pointer is pointing toward the node 10. Again we will check if statement, if list is null or not. No, list is not null. Now we will again execute the else part and call the function with the next data item, that is 20. And this process will continue until list become null or we reach the end of the list, because the next item in the last node will always point to null. So when list become null, we will return and continue executing the remaining statement that was suspended before. So upon reaching the base case, we will return and start backtracking and execute the statement one by one. So now list is null and we will return. The next statement of this function call is executed, that is cout list data. So here we are going to print the last item, that is 20. 20 will be printed. Now we will return to the previous function. To complete that function, we have to execute the next statement with the cout list data, and here we are going to print 14 and so on. 10 will be printed, then 6 will be printed, and that's how recursion works. It solves the problem and break the problem into smaller part until it reaches the base case, and after traversing or backtracking it will print all the element in reverse order. This is the dry run of the same problem that I have explained in the previous slide. Let's solve another example Fibonacci series using recursion. What is Fibonacci series? The Fibonacci series is the sequence of numbers like 0, 1, 1, 2, 3, 5 and so on. And the next number is found by adding up the previous two numbers. Now let's design the recursive solution of Fibonacci sequence. We need to determine two things, base case and general case. And what is the base case? We know that if n is equal to 0 or n is equal to 1, the answer will be n. So Fibonacci of 0 is equal to 0 and Fibonacci of 1 is equal to 1. And to find the Fibonacci of 2, we need to add up previous two numbers. So if n is greater than or equal to 2, we will sum up the previous two numbers by calling the function again Fibonacci of n minus 2 plus Fibonacci of n minus 1. But this will be our general case. After determining the base case and general case, we can write down the recursive solution of Fibonacci sequence. So what is the recursive solution? We need one if-else structure. If n is equal to 0 or n is equal to 1, return n. This is our base case. Else, return, call the function again with Fibonacci of n minus 2 plus Fibonacci of n minus 1. Note that in this example, we are calling the function 2 times in one statement. Here is the dry run of the recursive function that find the Fibonacci of 5. So n is equal to 5. There are two parts, if and else. If n is equal to 0 or equal to 1, we will return n. Else, we will call the function again. And notice there are two function calling with Fibonacci of n minus 2 plus Fibonacci of n minus 1. So Fibonacci of 5 is not equal to 0 or equal to 1. We will call the general part with Fibonacci of n minus 2, that is Fibonacci of 3, plus Fibonacci of n minus 1, that is Fibonacci of 4. Now we will execute these function call from left to right order. So we will solve Fibonacci of 3 first. Fibonacci of 3 is not equal to 0 or equal to 1. So we will call the general part again, that is two function call Fibonacci of 1 plus Fibonacci of 2. Fibonacci of 1 is reached to the base case because n is equal to 1 and this will return 1. So the answer of Fibonacci of 1 is equal to 1. Now we will execute Fibonacci of 2. Fibonacci of 2 is not equal to 0 or 1. We will call the function again with Fibonacci of 0 plus Fibonacci of 1. Fibonacci of 0 and 1 reach the base case. The answer of Fibonacci of 0 is 0 and Fibonacci of 1 is 1. Now we can add up these two numbers and solve the recursive call of Fibonacci of 2. So 0 plus 1 is equal to 1. So Fibonacci of 2 is equal to 1. Now we can compute the answer of Fibonacci of 3 because we have the answer of Fibonacci of 1 and Fibonacci of 2. 2 plus 1, Fibonacci of 2 is equal to 1 and Fibonacci of 1 is equal to 1. 1 plus 1 is equal to 2. So the answer of Fibonacci of 3 is 2. Now we have solved the left part of our problem. Now we will solve the right part of our problem, that is Fibonacci of 4. Fibonacci of 4 is not equal to 0 or equal to 1. Now we can call the general part again with Fibonacci of n minus 2 plus Fibonacci of n minus 1, that is Fibonacci of 2 and Fibonacci of 3. Fibonacci of 2 will again call Fibonacci of 0 and Fibonacci of 1. The answer of Fibonacci of 0 is 0, Fibonacci of 1 is 1, 0 plus 1 is equal to 1, Fibonacci of 2 is equal to 1. Now we can compute the right part, that is Fibonacci of 3. Fibonacci of 3, we will call two function again, Fibonacci of 1. 3 minus 2 is equal to Fibonacci of 1 and 3 minus 1 is equal to Fibonacci of 2. Fibonacci of 1 is equal to 1 that reached the base case. Now we need to compute Fibonacci of 2. Fibonacci of 2 will be divided into two parts. Fibonacci of 0 plus Fibonacci of 1. The answer of Fibonacci of 0 is 0. Fibonacci of 1 is 1. So the answer of Fibonacci of 2 is 1. And now we can compute the Fibonacci of 3. 1 plus 1 is equal to 2. So the answer of Fibonacci of 3 is 2 and the answer of Fibonacci of 2 is 1. 2 plus 1 is equal to 3. The answer of Fibonacci of 4 is 3, and 3 plus 2. The answer of Fibonacci of 3 was 2. The answer of Fibonacci of 4 is 3. So 3 plus 2 is equal to 5. So the final answer, the sequence number of Fibonacci of 5 is 5. So that's how we will solve the Dioron of recursive solution that call the recursive function 2 time. Now this is your home task. Find Fibonacci of 7 and show complete Dioron, and also find out how many function calls were executed. A recursive solution solves a problem by solving a smaller instance of the same problem. It solves this new problem by solving an even smaller instances of the same problem. Eventually, the new problem will be so small that its solution will either be obvious or known, that is the base case. This solution will lead to the solution of the original problem. So, while constructing recursive solution, you need to ask 4 questions to yourself, and how you can define the problem in terms of smaller problem, and how each recursive call reduce the size of the problem, and what part of the problem will serve as base case, and when the problem reduce, will you reach the base case or not? If not, then your algorithm will run in finite time. Recursion works best when the problem or the data structure support the recursive solution. If not, then there is no reason to increase the overhead on processor. Recursion is truly valuable when a problem has no simple iterative solution. Last 2 examples is your home task. Write a recursive solution of find function that will find an element from given array. You have already implemented the iterative solution of find function. To write down the recursive solution, you need to determine 2 things, base case and general case. That is already written on this slide. The base case of the find function is if array is empty, return false. And general case, if first element of the array is the given value, return true. That means you have found the element. Otherwise, you need to reduce the size of the problem. So skip the first element and recur on the remainder of the array. Similarly, write the recursive function that count the total number of element in an array. Base case is straightforward. If array is empty, return 0. That means 0 element are present. And recursive step, if skip first element, recur on the remainder of the array and add 1 to the result.